did we get more chalk?
Oh yeah, you know what? Start with what is there and I will ask that. I will.
Une blanche? Ah oui, super. Okay, so you know, I wanted to show you some a little bit of a proof. In fact, that's what Florent told me yesterday. I said, you know, what should I do now? And he said, just give a proof, of course, in the physics way, which means show a computation. But, so I'll look at the, just very briefly, in fact, at this last result. And, you know, I introduced this question of classification, information exponent, which allowed us to classify. We had this rank 1 models, let's say, on the sphere in high dimension. And I wanted to understand the how to, what I call escape mediocrity, how to escape the entropy at the equator and begin to correlate with the signal. So, so I want to maybe dig deeper a little bit in this thing, because this is not, I mean, the proof is technical, but not too hard, not too technical. Whereas the other one, that's for OGD. I will talk about OGD. OGD is much simpler, in fact, to analyze than Langevin or even gradient. So let me explain again what the setting was. So this is, of course, I should remind that it's a paper with Reza Ghessari and Okosh Jagannath. And it's in archive in March. Okay, so it's, so let me remind you what we're doing. We had, let's say, a family of distribution P indexed by a parameter x, usually called theta, but here it will be x. Let's say on RD, right, the distribution of the data. The parameter x here was chosen to be on the sphere. And here, for whatever reason, the sphere is like the sphere of physicists. It's the sphere of radius square root n instead of radius 1. Sometimes the normalization changed because of that. Then we have an m sample, a random variable yi, iid of this distribution. Ah, cool. Thank you. All right, and we will be here. I will just call alpha the ratio between m and n, as often. But this alpha will not necessarily be finite. It could diverge, as we'll see. And then we have a loss function, ln, from the sphere. Let me call this guy S sub n. It's the sphere. Sn cross Rd R. Okay. And then what we want to do is, of course, so we have the population loss, true loss, which in the paper is called phi. It's just the expectation of L of x and y. When you take y under this distribution, I should put an n somewhere. Okay? That's the true loss. And so, of course, we have the empirical loss. I will take again the notation I had before, which is 1 over m, sum of L of xi, I'm sorry, x and yi. Okay, and so of course the question is, what you want to do is find the minimum of this true loss, but then population loss, but then the only thing you have is the empirical loss, and you want to minimize this empirical loss. And understand if you do anything good with it. So we will assume here, so the important assumption here, this rank 1 assumption, if you want, the spike assumption, is that this phi, the true population loss, is in fact a function. Maybe I don't need to assume that yet. Let me just wait for a second before we do that. Of course, now I want to analyze so we try to minimize this by just using OGD. Online gradient descent. Importantly, the important thing, what I have in mind is with a random initialization. Completely no information in the initialization in X. Yes? Between what and what?
So what's the inference problem? You have y that are drawn from...
What I want to do, okay, so maybe the notation is, okay, I could have done.
It's not a relationship between the yi and the x.
Just a second. So you have these distributions on RD, okay? You have a sample, and this inference problem, the natural inference problem, it's a parametric statistics problem. You want to estimate X, the parameter. Yes, X is theta if you want, but I don't like theta, so I use the X's. Okay, so you want to estimate X, learn X, okay, and you have a sample, and you do that with whatever loss function you like. Okay, for the moment, the assumption will be that this is a rank 1 situation, a spike situation, that you have a true. The assumption is that you have a true X, an X star if you want, okay, which again, that you want to learn. Okay, so again, I draw here the sphere, and the true X, the X star, or what I've called V before or whatever, will be here always almost my North Pole, okay, in the picture. So that's what we'll put later, but at this point I don't need to do it. So, of course, I write again the OGD, so one version of it at least it's this evolution in discrete time. Xt is xt minus 1 minus the step size, the gradient of this L at xt minus 1, and y, where did I put the index here, yt. Right, so you take the last, it's online, so you just take the last sample point, you put it there. This is the spherical gradient, and then, but this still, even if you take the spherical gradient here, of course, this doesn't stay on the sphere because this is not really I could have, instead of writing this, I could have written, I follow the flow of this vector field, and then I would have stayed on the sphere. But this, of course, doesn't stay on the sphere, so you have to, this should be x tilde, and then you have to normalize it to put it on the sphere. Okay? That's not good enough because for crazy reason, we've chosen the sphere to be square root n, so I multiply by square root n. Okay? Again, this is a detail. If you're more of a geometer, instead of doing this, you just follow the flow of this gradient field and on the sphere, and you stay on the sphere. Okay? But that's more elementary. Okay, so delta is the step size, and you start from x0 to be whatever, point x0. What I have in mind is to assume that x0 will be distributed according to uniform on the sphere, for instance, but it could be whatever. We'll see. We won't treat only this. Okay? So before I go, I should draw this picture again because it's crucial to understand this question. Everything here is about the initialization. I'm interested really mostly in the weak recovery, as I explained. How do you get away? How do you do better than random? So as I explained here, if I'm in the sphere of radius square root n, if you take a point at random, it will be essentially concentrated on near the equator at distance little of 1, essentially, because I multiplied everything by square root n. Okay, so if the radius here is square root n, so all the mass of the uniform measure is here, okay, at this distance. If you had the usual normalization, this would be 1 over square root n. It is crucial to understand, and we will see that if I started from so I will call the latitude m of a point on the sphere will be, let's say, the first component here, x e1 divided by root m. Right? So that this latitude is between -1 and 1. Right? That's this altitude. This is a fixed latitude. All right? So so here I'm starting with an m which is of order 1 over root m if I take a random point, and that's the best I can do. It's crucial to understand that if you start with an m 0 at time 0, which is epsilon positive, right, but not depending on n, this is an easy problem. Okay? As we will see. The hard part is to start from a very, very tiny initial point. Okay? And so if you start from here, this is a hot start. And it's not, and essentially things are much simpler, as we will see. The problem really is when you start close to here, as I described yesterday, which is where, when you have no information, that's where you start. And so I love the following picture that you may have already seen. This is really not the way to see a sphere in high dimension. Okay, a sphere in high dimension is like, the way I see it is like this. Okay, all that is the equator, this region, and these two things are the poles. Not the pole, the hemispheres here. Okay, that's the way you should see it. And with the true equator somewhere here. Okay? So if you think like this, you understand what I just said. When you start with a point at random, you start with a point at random, let's say in this big region. Whereas if you start with a hot start, you start in fact here. Okay, and what you want to find is maybe this. So you see, much, much easier. Okay? That's if you have this picture in mind. All right? So now, what is the question I was describing? So, of course, we will see. We will have, of course, a gradient flow or an n-line gradient flow, whatever. We have a vector field. And so this vector field here, of course, in order to find these things, will point to that. So you should see this thing with a little slope. You have a little slope. It's like a golf course, but with a little slope. And the real question is whether the slope is strong enough to allow you to come close to this. As soon as you are here, as soon as you've climbed here, you're essentially done. Okay? So that's really the picture. I'm insisting on that because it's sometimes very hard to find in papers that the initial point is that you have a hot start. Okay? And the techniques to deal with a hot start are much simpler. Not much simpler, but are simpler. For instance, the natural approach of physics that I have described before, based on the mean field, Cogliandolo, Kurchan, Chris M.T. Horner, etc. approach, which consists in letting n go to infinity first and then t go to infinity, cannot deal with this situation easily. The information you need here is more than that. Okay, so you need something which is, so what we get, of course, is, as I said, we use all sorts of inequalities to deal with some, we get a less precise result maybe. We don't have the description because this, but we get what we need to know when we can get out of the equator. Once you're out of the equator, then the Cogliandolo-Kurchan type approach works. Okay, so we need assumptions. So the first assumption that we will need is that this true population risk here, this the rank 1 thing, should be a certain function of the latitude. That's what we assume, right? So you have this hidden spike or vector, and your true population risk is like this, okay? And as you remember, tensor PCA, matrix PCA, P plus K model, the The GLMs with a spike are like that. Okay. So we need assumptions on the regularity of the loss function, which are not strong, not very strong. For instance, they include every function that is smooth, of course, but they also include ReLU, for instance, which is not completely smooth. Okay. So the regularity assumption you need is that. Okay, let me forget them. They are not crucial. Yeah? Not at all. What? No. We don't care at all about that. What we will care about is the behavior of this function near. So, as I explained last time, the only important thing is the behavior of. The crucial thing is the behavior of this phi near m equals 0. Okay, that's the only thing that counts near the equator. And you remember we had this classification into different information exponents. That's the only thing. Of course, models are not convex. Okay. So what I want to get is weak recovery. What I'm aiming at is weak recovery, and so which means that there would be a certain positive number eta such that the let's say the limit when n is large of the probability that, let's say, okay, I'm sure, so my estimator, okay, maybe I'll write this later. Let me just say this in words. Weak recovery, I want that after my m steps, since I have m sample, after the m steps of OGD, I want to make sure that the latitude of my x at the end of this is positive, is somewhere here, is right? So correlated with the signal. I'm not asking for full recovery. I don't ask for this m to be 1. Okay? Just so in my picture with these two little holes, I want to make sure that I've fallen into one of the little holes. Why did I draw it like this? Of course, because again, the mass, with the uniform measure, the mass of the two hemispheres, if you put a distance epsilon, is exponentially small. Right? So they are really tiny. Okay, so all right, so I will need I will define one thing, which I will call the sample-wise error for the loss. It's the following thing: H0L of x is the loss taken at the L sample minus the mean of this, which I call phi of x. Right? So a simple thing. So for every point in my sample, I look at the deviation for the loss value at this point minus its mean. Okay? And I call it H, 0 L of x. Why H? Of course, because if you remember the example of tensor PCA, this was something like x1 to the p, and this was the Hamiltonian of a spin glass. So the Hamiltonian has stayed in the letter H. Okay, that's the random part. Okay. So we need assumptions on this, but so if you look at the paper, we need the assumption on the fact that H0 scales, we call it scales naturally. So I could explain that, but that's not very important. Let's say it scales this. What I mean is that if you look at the gradient of this H0, okay, that's a vector field. And you want this vector field on the sphere to behave like it's a random vector field, and you want it to behave like it's a real random vector field. Okay, so that's the assumptions we have, like it's either uniformly chosen or something like that. So let me tell you okay, maybe I should write what this is. But they are satisfied in every example we've looked at. So we need a bound on that, and with the normalization we have here, it should be this. And we need the natural bound on the norm of the gradient, to the power 4 plus epsilon. Let me see. Okay. So
I don't know what that means. Epsilon came naturally. Could you repeat that?
it means that. Okay? Just that, these two assumptions. That's the assumption, okay? So why do I mean that this is a natural scale? Is it because if you chose here instead of the gradient of this function, you chose a vector, right? Gradient is a vector, right? Oops, a random vector. If you choose a random vector with IID component, you should have this scaling. Okay? Good. Anyway, in all the examples I've mentioned, it's like that. Okay, so now, remember what I introduced, what we call the information exponent? That's a little bit, that might be, this is what we found as a title. Whatever else would be good here. Remember, it's simple. You look at this function phi, the true population, and you look at how many derivatives it has at 0. 0 is the equator, that's the important region. So you say that the information exponent is k. That means that that this function phi is smooth enough, ck plus 1, or minus 1, 1, and that the derivatives of phi at 0 are all 0 for L between 1 and k minus 1. And the k derivative is not 0. In fact, in our case, we will ask it to be negative, so that it will point in the right direction. And then you have a bound on the other derivative. Okay, so that's the important thing. So the case, so if your phi of x behaves like x to the k is the information exponent. Okay? All right. Now, first thing, it's important to realize that this information exponent is not a property of the data, nor it is a property of the loss function. It's a property of the pair. If you change, it's of course the whole statistical problem you have is the distribution P and the loss L, and this pair defines this K. For the same P, you could change the L, and we will look only, and I should have said that, we will look only at P which are Gaussians for the moment. Yeah.
Assume the case derivative is negative. What if it is positive? Then you're just not.
Yeah, so let me say, this is just to escape this kind of question that I said. So let me explain. I want to avoid, as we know, there are questions of parity. I don't want to begin having trouble with parity. So the only thing I will do is look at at one side, right? And I will start on the equator, but on one side, and wonder whether I can go on the positive side. Of course, this doesn't change anything. It's a factor 1/2 or whatever. But this just do not have the nightmare of the parity. So this is what. So I want this to point up there. When you start from here, I want the gradient of this to point up there, so that you have a chance to reach that. Okay. But of course, in some cases, depending on the parities, the symmetries of your problem, when you start like this, you could go this way too. Okay. But I don't care, because I will only treat half the problem, and that's quite enough. Okay, so what do we want to conclude with all this? So if we have this regularity assumptions, whatever, and we know the information exponent, remember that what I was saying is that we can conclude about weak recovery and about the two parameters of our problem. In fact, we have three parameters in our problem. Once you have fixed the loss and the data, once you have your problem, you have three parameters. Where you start, the x0, the delta, the step size, and of course the amount of data, the alpha. Okay? So what do we have? So in our theorem, 1 in the paper. Oh no, I forgot what the number is. The first theorem stated in the paper. So again we have an m, which is an alpha, maybe an alpha dependent on n. And so I assume that my pair loss has all the properties above, is admissible, scales naturally. Admissible means regular enough and scales naturally. But again, all the things you think of, all those GLMs fit in that, and has exponent, information exponent k. Okay, then we have the following. So so now pick a sequence Bn that goes to infinity as slow as you want. Okay, so this Bn is just there to have a little bit more than a constant, but whatever you want. Okay, so of course it means in practical terms it's a large constant, right? It can be log n if you want, all right? So if Bn goes then, so first case, the easy case, that is k equal 1. Then we have the following thing. If you choose your alpha n to be larger than Bn, okay, for whatever reason it's Bn cubed. If Bn is very slow, grows very slowly, Bn cubed too. And the important thing is here, if your delta, which is delta n, is between Bn over alpha and 1 over square root of Bn alpha. So of course, this condition here is made such that this number is smaller than this number. Right? And then you have room in between. So when you choose your step size like this, then there exists an eta, a positive number. There exists a time, t, which is less than m. M, of course, remember our OGD process here is limited in time by the number of data, so it has to stop at m, right? So here there's a time before the end of this process such that the limit, when n is large, of the infimum over the x0, the initial point, such that the latitude of x0 is larger, so as you see here, than gamma over square root n. Okay. So this means I'm in the upper half hemisphere, but I'm a distance here which is typical of a uniform choice, of a random choice. But look that I'm giving here an inf, so it's a worst case scenario. It's uniform in this. Okay? I cannot, I mean, of course the bound would depend. If I allowed here this to be even closer to the equator, we analyze that too. But then it depends on how close you start from the equator. It's harder and harder to escape the equator if you start very close to the equator. So this is an inf, which is good, and as you will see, and then the probability starting from x0 that your OGD, so now you look at this, the latitude of your OGD at time t, m of xt is the latitude between -1 and 1, and here between 0 and 1, that the inf of that, when t is larger than your capital T, that this is larger than eta, this is 1. So let's take time to swallow this. So this tells you when n is large, whatever your initialization, which is not too close to the equator, after a time t, which is fine, which is smaller than m, so beyond the reach of what you're doing, then your latitude is above a level eta. Being at level eta means you're somewhere here. Okay? And then not only do you reach this level, but you stay there. You stay above that. It's the infimum. You stay there. Okay? So this is weak recovery. Okay? And so what I'm saying is that the probability uniformly in your starting point in this region that you have weak recovery is 1. When n goes to infinity. Yeah? Gamma is whatever number positive. Okay. This just measure. The important thing here is the scaling, square root n. Of course, when you fix the t and the eta depends on gamma. All right? So this tells you you have weak recovery as soon as you have that. Yeah?
You know our t depends on n. How long is this time?
Yes, we do, but I forgot. Yes. Yeah. This does not only depend on, it depends also on the choice of the delta you've done in this window. So in fact, it depends on delta times alpha square. And I forgot how it's, but it's a function of delta times alpha square. Okay? Yes.
Don't you want to ensure that T and eta depend on gamma in some way that, like, for instance, there's a limit as gamma goes to 0? Like, if, for instance, eta goes to 0 with gamma
Wait. No, we do that, but instead of giving a big theorem, which is a little bit of a pain, I will give the thing that is really useful for in this thing, because the only thing I'm interested in is if I start randomly. And we have the same information if we start randomly. So here it's a worst case scenario. I can have the mean scenario. No. Typically, when you start randomly, you start at gamma over root n with a random gamma. Okay? That's the central limit theorem. Okay? Gamma is Gaussian, right? But Gaussian with a fixed mean zero and a fixed variance. So in particular, then, when you start randomly, so if now you start, if x0 is chosen uniform on the sphere, then you have the result, limit n, probability, let's say, call it mu n, the uniform law on the sphere, starting from the uniform law, that the infimum f of xt after a certain t is larger than eta is also 1. Okay, so this is really what I wanted initially, but the proof we have is better in some sense because it gives something fixed. Again, if you start with m0, which instead of being a constant divided by root n is a small constant, this is typically what you find in many papers, and which is, of course, already interesting. This is the regime where you can apply directly Couglie-Landau-Locochan type things. Okay? The hard part here is to go from 1 over root n to epsilon. Okay? Yeah.
But my eta and t have a properly defined limit as epsilon goes to
No, I really believe I really believe no. This is an old problem. It's always the problem of Couglie-Landau-Locochan that we have faced, even when you studied spin glasses. Why this approach was hard? Remember, when you study this limit, which is first n and then t, going to infinity, you have this infamous matching problem, right? The longer time behavior. And something similar here. The beginning, if you start from very low, the beginning is really not captured by that. That's what I'm saying here. And so we don't give a closed equation as neat and nice as Couglie-Landau-Locochan's equation, but we give enough information to know that we escape the equator. That's the important thing. So that was k equal 1. That was the easy case. So this is easy. Why? Because essentially, if you assume that Bn is a constant, because log n is a constant, then your alpha has to be large. And in fact, I could give a theorem like this. Why do I need this to diverge? Maybe here, just to prevent. If I have written this? Yes. Here, the way I state this is I want this probability of weak, this is the probability of weak recovery. I want the probability of weak recovery to be 1. Okay? If I allow for a little bit of error, if the conclusion I want is the limit, let's say inf in n, of the infimum on the same thing, of m x0 larger than gamma over root n, of the same thing, the probability of the infimum, etc., larger than eta, the same event, the recovery event. If I want this to be just larger than 1 minus epsilon, right? So I want the probability of recovery to be almost 1. Then I can do that. So the statement is, so sorry for that, this is mathematics at its worst. There will be something like 6 quantifiers, but so for every epsilon, there exists, and I even forgot gamma, but there's an eta, there exists an alpha 0, such that for all alpha larger than alpha 0, there exists a delta and a t, such that this. All right, so. What? Yeah, sure. Here. Okay, so what does that mean? Once I've chosen the error I'm allowed to take, I want to have, a probability of 99%. Then this eta, of course, is the level of the recovery. That's okay. But there exists now an alpha 0, which is positive, doesn't diverge. So you don't need the log n here. Okay. So so that as soon as you have that much data, then you can find the delta and the t, such that this will happen. Okay. So this means that you have weak recovery with 99% probability with a fixed alpha, right? With an amount of data to be just a fraction of n. Or fraction, a multiple of n. Okay? If you insist to have 1, you need a little bit more data. Okay? That's the result for the easy case. So the easy case, if you look at it like this, it's really easy. Right? It means everything's good. Okay. Then you have the critical case. Oh, by the way, in this case, you also have a limb soup. Okay, you have also a negative result in this case. That is, for every eta, so whatever the level, there exists an alpha 0 such that for every alpha smaller than alpha 0, and for every delta which is of order 1, then the limb soup of the soup of the same argument, of the probability that the inf is, that the soup of m is larger than eta, is smaller than epsilon. So this tells you that whatever the level you want to define weak recovery, if you have too little data, there is an alpha 0, which depends on eta, but if for every data alpha smaller than that, so if you have too little data, whatever your size, the size of your step, then you don't recover, but worse than that, you never go above the level of eta, you stay below. Right, so bad situation here. Okay? So this tells you that in the easy case, if you have, there exists an alpha 0, such that if you don't have enough data, you won't recover at all. Your trajectory will never go away from the distance. Okay. Now, let's go to the critical case. So I remind you, this critical case covers a lot of the nice problems. Okay. Phase retrieval, whatever. Oh, when I said mixtures of Gaussians, by the way, I was wrong. Let me just say that, maybe I'll come back to that. But imagine you take a mixture of Gaussians. Okay, that's what your data on RD. But your, let's say the mean of your, the two Gaussians have the same variance, say the identity. Okay, and the centers of those two Gaussians, like Florent was drawing this picture, are, let's say, 2 points which are antipodal on the sphere. Right? You have x and minus x, like he said. Okay. And now your mixture, the thing you're looking at, the distribution, is a mixture of these two Gaussian. You have still to define what the proportion of the mixture are. So let me call that P. So you have P times this Gaussian plus 1 minus P times that Gaussian. Right? When P is not a half, this problem is easy. The exponent is 1. Right? So it falls under this. When P is a half, this problem is critical. It's like phase retrieval or whatever. Okay? So You don't need to go very far to find this kind of distinction here. So of course it's harder to distinguish when your mixture is just symmetric. Okay, so here k equal 2, now you have to choose an alpha n larger than my bn, my famous log n cube. And the important term is log n squared, as I explained. And then you need your delta, as before, to be between 1 over square root of b and alpha and bn over alpha log n. Okay? Yep. This is exactly what I'm telling you. Forget convexity. This has nothing to do with convexity. Oops. Okay, but this is it's still hard to escape the equator. It's just a matter. Okay, forget convexity. Take Brownian motion on the sphere. Right? You can't make a more convex flat landscape, right? And you want to find this point. You won't. You just can't. So that's the needle in a haystack. Now, take Brownian motion in a sphere and put a harmonic potential with the North Pole, right? You will be able to find the North Pole you want to find it in short time, remember? You will find it only if the curvature, if your curvature is strong enough, because you need the drift to be strong enough there, right? So harmonic, good, because the gradient is linear. So at the equator, it's k equal 1. But now take a potential that is like power 4, and you won't escape the entropy. In fact, this has nothing to do with, the landscape and whatever. It's just escaping the mass at the equator.
Clarify, the two Gaussians, you have the two clouds, but you don't have the points labeled, right? You don't know which point belongs to which cloud.
Of course.
And you have this for your thinking of the other thing.
But it still allows me to mention very clearly that this has nothing to do with it's a completely geometric problem which has nothing to do with landscape. It has to do with entropy. Okay? Again, if you take a random walk on the cube and you want to find the point made of all 1, it takes a time which is exponential in n, if you just take a random walk. Now, if you put the question we have here is, you put a little drift to go to the point, let's say, made of all 1. How much drift do you need to get there in short time? That's exactly what we're doing here. Okay, so now here, this is what, and then this implies the same weak recovery result as before, the same statement. And now when you have k equal 3, so first, what does this say? This says that essentially here you need log n squared for alpha, that is, you need a little more data than finite. Okay? And for k larger than 3, that's the hard case. Remember, tensor Pca. Then to have weak recovery, you need this. Again, that is crazy Bn cube. But then you have this log n squared as before. But you now have n to the power k minus 2. And you need delta to be exactly as before, 1 over square root bna alpha, and like here, bn over alpha n, and to the k minus 2 over 2. Okay, so you have the same result of weak recovery under this. So now the important thing is this. Now you need very much more data. You need a polynomial amount of data. And this is what we saw in the tensor Pca. We needed, our lambda was supposed to be, the exponent was k minus 2 over 2, because there was a square root somewhere. Okay? Good. So these are the positive results, right? They tell you if you have a hard case, if you have enough data, and you choose a small enough step size, the right size of the step, then you have weak recovery, etc. Now, you could ask, maybe all these results are just limited by the power of the proof. So are they good? And so in order to show that they are decent, let me give you refutations. Right? That goes with that. So this tells you if you have enough data, you choose well the step size, you weakly recover. Then I want to say you don't recover if you don't have enough data. So let me be a bit faster. If k is 1, if your alpha n is smaller than your, so remember Bn was going to infinity as slow as you want, so this is going to 0 as slow as you want, right? So if you have then, and delta is of order 1, or for case equal 2, and if alpha n is less than log n times this, again, treat Bn as a constant, and if I replace the 1 by 1 minus epsilon, I could do that with a constant. And delta is order 1. And then 3 in the case k equals 3, larger than 3. And alpha n is less than this Bn n to the k minus 2. And alpha delta square, that's the important thing, is of order 1. So this is the answer I was giving, when we were asked the order of the time, and I said it depends on this alpha delta square. Then you have, for every eta, the limit when n goes to infinity of the soup when m at time 0 is less than, let's say, a certain gamma square root n. So for every eta, for every gamma, of the probability starting from x0 that the soup, so that's the refutation, soup of xt larger than eta is 0. So this tells you under these conditions, the probability that your trajectory gets away at distance eta, there's a weak recovery, goes to 0. Okay? So your thing just doesn't work. Okay? Yeah, alpha times delta square is over order 1 here. That is, you want delta to be of the order 1 over square root alpha, which is okay. So the real thing, so remember, what should I, yeah. Yeah, so remember that in the easy case we have, and I will tell you more about that, we have plenty of things, right? If you take the GLM with an activation which is reasonable, it will always be on the easy case essentially, or critical. Okay? And then, as I said, in the critical, we had the spike matrices, we had the phase retrieval, etc. So the real question is, does this case happen, or is it just a pervert thing to look at because we like difficult things? So of course it does happen because I showed you we started with a case like this. The tensor Pca was there. But the real question is, does it really happen in decent examples, right? And we'll come back to that. Okay, so enough of results for the moment. Let's so how does this work? So let me, in order to explain this, let me just do first a complete ridiculous caricature of that. Let me just assume that, in fact, I know the true population, right? Then things should be easy. Okay? I know the true population risk. So I look at the gradient flow, the online gradient flow, in the landscape defined by the function phi of m. Okay, the true population risk, not the empirical risk. Okay, so if I do such a thing, of course it doesn't mean anything here. and I project it in one direction, right? And I can because the population risk is a function of one variable, m, the latitude. So I can just follow this variable, and that becomes a trivial thing. Then my online thing would be this gradient of phi, what I call phi at time xt minus 1 times the gradient of m at time t minus 1. And so, okay, that's a trivial fact. So this is like, it's easy to compute this gradient because this is a function of m. And it behaves essentially when x is, when you're at the beginning of this trajectory, when x is close to the equator, this behaves like m to the k, right? So with maybe a constant. Okay, and so the gradient will give you m to the k minus 1 at time t minus 1. And I'm just computing the derivative of m to the k. And then I have the gradient, this gradient of, of this thing here. This whole thing to give me that. Okay? So if you accept that this would be it's a trivial fact that this kind of equation drives this thing. Let me keep it like this. I don't want to keep that. So then it's easy to see, this is completely trivial, that if you start with an m0, which is a small, let's say negative power, for us the zeta will be a half, but you could start from anything in this trivial problem. Then it's clear that when k is 1 or 2, when k is 1, let's say, the time to recover, weakly recover, that is the time for this m to reach a finite value, is linear, something like this. When k is 2, it's quasi-linear. This is something there's a log. What? Yeah, because I mean, okay, in fact, this is true, right? Because your phi was, okay, maybe what I wrote before was not true. Yeah. Yeah. No, but in fact, yes, this is the right answer. You just, this phi was mt to the k, essentially. So this is what we get. All right, and then if it's larger than 3, all that is obvious computation, then it's polynomial. And you get something like this, n1 plus, if I'm not mistaken. Anyway, this is an obvious computation, everybody can do it. So the thing is not a mystery, it's just a 1D thing, and where m0, the vector field, if you want, is 0 at 0, whether it's you have a derivative to push you away, or a second derivative to push you away, or a third derivative to push you away, will make a difference. Of course, if you start really from 0, you won't move. But if you start a little bit away from 0, it takes time to get away. Okay? Good, so that's, okay, intuition. Now if you want to do the beginning of a proof, you do this. Of course, so we will see here that the randomness doesn't help. Okay, that's of course what we try to prove. So, at least in those time scales, it's always the same thing if you give enough time. So here when you look at the true problem, you can see something like this happening. You have something of the same nature. I hope I didn't make a mistake in the sign. Maybe I did. Okay, plus or minus, I forgot. And then you have, then comes this thing that I call the, here I'm forgetting the step of the projection step. I'm just looking at the first step. Okay, the projection of the sphere, for the moment I don't care. And so remember, this was what I call the sample wise error, whatever. and it comes here. So you have something like this with a stochastic term, right? This is exactly what Alice was saying. There is noise, of course, in our system. The noise is just that. So this tells you why we needed some, when you need some assumption on the regularity of this and some bounds, because you want to control that. Okay, so if you follow the trajectory of this, and you look at the cumulative effect of that, because if you sum all these guys, right, just to understand whether they are, what kind of role they play, and you call this MT. So all the you sum all these guys. This is a martingale, and you need to do a little bit of so. The absolute, of course, in order to control it, we really work a little harder than that. There are quite a few pages that you can read, but just to understand what's happening, you just apply the Doob inequality to this martingale. Right? A martingale, you know that it cannot be too large. Then you find that it's of order, if I'm not mistaken, with all the constants here, delta square root t after time t, square root t here, divided by n. Under the assumptions we had on the regularity of those guys. Okay. So now what we're saying, what I was answering at least, is that this random part, in the positive results, of course, you want to prove that this random thing does not play a role, right? This thing which, okay, you have this motion which is in 1D, you try to go to the North Pole. This thing moves all around, could also move around the sphere. It has no reason to be aligned like this. It does whatever, it's random. And you want to say, I don't care, because if I don't care about this one, then I'm back to the problem I was giving before. And then for this one, you know how much time it takes to escape. And then it's just a matter of classical probability to prove that the random trajectory will also weakly recover as this one. Okay? So, so the question is, so you have this order here, and for this to be negligible, what you need is that you need this. You need that at time m, let's say, which is the final time, the maximum you can do. Right? So the order of this, all along the trajectory, should be the same order as the m0 that you started. Right? At worst. So, okay, you look what that means, and essentially this gives you the intuition about all the results, the alpha and the delta that we have. Okay, this is far from being a proof, but but it's essentially a proof. You understand that the only thing you have to control is this martingale term, seriously. Now, this is not new, of course. This is old as hell, because that's called the Ode method in approximation and whatever. So if you want, I mean, it goes back, in math, it goes back a long time, but if you want a good, and in if you want a good account of that, you have this paper in 77 and a very nice course by Michel Benaim in 99 in the seminar of probability. Okay, so this gives you all sorts of things like that, where you have an ODE, not necessarily an ODE in one dimension, which is here the simplest thing you can do. The dynamical system here is in one dimension, and then it's perturbed. You could do something in whatever, but all these things are in fact, so they are much more precise than all this, but they are in fact dealing with a situation where the ambient dimension is fixed. So you don't have, whereas here the ambient dimension is diverging. So you don't have this problem of entropy. In fact, that this one has this one has one dimension, but this one has very many dimensions contributing to it. Okay? So that's what has to be done here. So so what these works do, they prove convergence in finite dimension. They prove convergence to the solution of the population dynamics, essentially. That's what we're saying here. You have this population dynamics, you have this random dynamics, and you prove that they converge. Okay, so There are, so just to come back to what's important here and what was not there, there are other methods to do these things. There's called the diffusion approximation, right, which is also pretty old. For instance, here's a paper that does things related to that in 1976. This is also done at this time in finite dimension. Now, if you want things that are, and so here the methods really do not apply. You have to tame this entropy. If you want things that work in high dimension, there are more recent works. And for instance, one by Tan and Vershinin in 19, so much more recent. And this is about phase retrieval. So it's one case if you want. It's not this. It doesn't. They do it on the sphere, but also on Rn. I mean, a more general situation. But the case is phase retrieval, so one of our critical cases. And they do, in fact, better. They do the natural thing, which is to prove a functional law of large number, a functional central limit theorem, and but that's for MT, for the latitude, right? But that's not what. Again, this is an approach which is, when you can do it, is much better because you have a limiting thing. What we do here is something which is valid in a much broader range, because we do inequalities, right? Something that's seldom done in the physics literature. We really just bound things. And enough, of course, we can't get the optimal things, but we bound things. It's easier to bound a much wider class of things instead of proving. But of course, extending the kind of thing that Vershinin and Tan do in this paper to all the cases I'm describing here would also be interesting if somebody is courageous enough to do that. Exactly the same thing. Let's say they do more, but they do it for phase retrieval. The phase retrieval is absolute, not the square, the absolute value. And they prove also weak recovery, but they prove something more. They prove really a law of large number. Yeah. And they I think, I forgot now, but I think they also have a CLT. Okay. Okay, so the inequalities that we use here, I won't go into that. We discovered them when we did this thing on tensor PCA. There it was hard. We didn't have a choice in tensor PCA to do limit theorems, so we had to have inequalities. And so the inequalities, you find them in the paper before this one with the same authors, called this algorithmic threshold for tensor PCA, would just appear. Okay, and then of course you have a huge literature on this kind of thing. I look at the paper, we quote quite a few. There are a few that I like papers by Wang and Lu and Mattingly on sparse PCA, which do things of this nature. And of course a paper by Sao Manelli, Giulio, Chiara, Carmelota, Florent, Lenka in 19 on the spike, on the P plus K model, the spike matrix and spike matrix tensor models. Okay? In this paper, if I understand well, in your paper, you do what I said before. You start with a hot start, and then you let the hot start go to 0, right? That is, so there you can use the full strengths of Gaussian, and then you have, in some sense, a more explicit description of everything. Here we just bound. We say we have this trajectory, 1D, and we bound how far the real system goes away from it, but starting from a random point, starting from closer to the equator. Okay? So, just examples of that, just to, let me to come back on this. Let's take our GLM as I described them last time. So, in this case, this phi of x was something like this, if I'm not mistaken. I forgot the notation I used for the activation function, but let me call it f. And so it's something like this. So here we have this E1 square. Okay. So that's the spike. I called it V star before, I don't know, X star, whatever. It was the spike. Here it's E1, or V, I forgot. And so we had, this is the L2 loss, right, the function I call L2, whose complexity I showed last time, and this work is on Antoine and Giulio. Sorry for that, Antoine. And so this is a function, and you may ask yourself, okay, so f is the activation function, right? And here A is distributed as Gaussian. Our entries are Gaussian. Okay? And you may ask yourself, for what f is this easy, critical, or hard? Right? It looks like a hard question when you want to differentiate at zero this mess here. But in fact, it's a very simple question. Too bad that Florent is not here because it makes fun of the fact that I like Hermite polynomials. But here, this is entirely a question about Hermite polynomials, even if it's not written. So this function can be written explicitly. It is, in fact, a function phi, as I said before, of the latitude. And this phi, so the true population for GLM is this. And this phi is, in fact, I forgot why there is a 2, but okay, maybe there is a 2. Sum of uj square, 1 minus m to the j. And what is uj here? Uj, of course, depends on f. And it's just the jth coefficient of f in the Hermite polynomial expansion. Right? Easy. So that's the that's f inner product with Hermite, or let me put a small h, in L2 of the Gaussian. Okay, so you take L2 of the Gaussian measure on the line. That's the L2 inner product in L2. You take the J's Hermite polynomial. Take the inner product with f. This gives you uj, which gives you this thing. And so, of course, with this formula, you know when the system is easy, critical, or difficult, right? So if, and it's an if and only if. So if U1 is non-zero, then the system is, my exponent, my information exponent is 1, and then the system is in the easy phase. So the things I gave you before. Right, if U1 is 0 and U2 is non-zero, and those Hermite polynomial, then K is 2, and it's the critical one. And if U1 is and U2 are 0, then K is larger than 3, and then it's hard. So, in the end, after all this mess, you have a very simple criterion. Compute the Hermite expansion of your activation function, and it tells you, of course, I said before that the information exponent is not a property of the loss function, but it is property of the pair. But here I assume that it was Gaussian, of course. Right? And if it's not Gaussian, of course, it won't be the Hermite polynomials are there because I assume that things were Gaussian. So examples of all that. When you take the activation function to just be x, add a line if you want, whatever, linear. Then, of course, this is easy. When you take to be sigmoid, it's also easy. When you take relu, all these cases are easy. And by the way, relu, even though it's not differentiable, satisfies the assumption that I've hidden on the regularity. Okay, we didn't ask for the function to be smooth everywhere. Okay, so all this fall into the theorem I described. All these things are easy, and you have the easy consequences. I mean, the consequences of the easiness that I gave before about weak recovery. Then now, what if you take f of x to be x to the k? Okay, we had x here. Okay, compute the Hermite polynomial. if k is odd, the first Hermite polynomial will not be 0. So this, if k is odd, this will be easy. Which is, of course, what we... Oh, this, I'm sorry, this k is not my... Sorry for that, because k was the information exponent. Kx to the L. If L is odd, the problem is easy, right? Like it was with for x here. When it's even, in fact, it's the first Hermite thing will vanish, so this will be critical, in fact, and you can typically, and you can prove that it's not hard, right? Because to be hard, you need to kill the first two coefficients, and you can't do that with a monomial. Okay? So if you really have perverse intentions and really want to find the hard things in this model, what do you have to do? So this is really to show you that it's hard to be hard. Of course, if you take f of x to be degree k, but the Hermite polynomial of degree k, who wants to do that? If you do that, then it will be hard. Right? Of course, if k is 1, it will be easy. Let's say take k larger than 3, this will be hard. Okay, so this tells you, of course, this tells you a little bit of something about the way you choose. I'm sure this can be extended to other initial distributions. The way you choose your activation function should be smart with respect to your initial distribution, right? When you take your initial distribution, so let's see what the recipe is here. Of course, what I'm saying now is pure. These are theorems, but what I'm saying now is guessing. If you take another initial distribution, let's say IID entries, but something else than Gaussian, you will have an orthonormal basis associated to it. Right? And so probably you don't want your activation function to kill the first two modes. That's what it says. Right? If your activation function here is H3, the third Hermite polynomial, it kills the first two modes of the Gaussian, and then it makes the problem hard. Okay, so that might very well, I have no clue, but that might very well be of more generality. And I don't want to prove it, so if you are interested, please do. So, so of course, when you take, so let's take one example of a non-too easy case, so that's phase retrieval. Of course, you could also choose absolute value of x. That's another version of phase retrieval. And you remember when Florent talked about it yesterday, he said you just need even. Remember that? He said even function. And the reason is this, in fact. So here, you take the phase retrieval like this. Then, like in Verschinin, and we find that the alpha n should be log n. And yeah, so for what is already known also, that's Verschinin, Town Verschinin. And then in this paper by that I just mentioned by, I forgot your first name. What? Stefano, okay. Florent, Lenka, and maybe somebody I'm forgetting now. Yes, sorry for that, okay. Oops. Then that's the P plus, in the P plus K model or PNK model, when P is larger than K and K is 2, you have something critical, right? Remember why? Because the loss function in this case was essentially x1 to the K plus a spherical spin glass. So the true loss function, the population loss function was x1 to the K essentially. And then you would, so when K is 2, it's critical, okay? And then in this case, indeed in this paper, when you start with an M0, which is positive, you need something like log n square, if I'm not mistaken. So in this case, so it might be, so look at what I gave in the result. The result I gave was log n square. Right, so similar to this. In this paper, they do better. right? So maybe in this paper log n is enough too, I have no clue. Not little o of log n, because in this paper I just mentioned, there's a proof that if you're little o of smaller than log n, it won't work. Even for this simple problem when you start with a hot start. But maybe log n, this is another question, since I'm giving question. Even in this simple context, maybe this would work, right?
That's because of the online, right? What we do in our paper is batch, and there we just see the codes.
I see. Ah, yeah, but I'm asking for online. Okay, so I don't know. There I'm not sure. I'm not sure that log n would work. I'm just asking. I'm not suggesting that it works. I don't know. There are some cases I don't know. This becomes a little delicate. Right? But if you want to train your muscles at this, you can. So of course, our result in this thing gives the same log n square, but when you start from m0, which is 1 over square root n, I mean, a uniform, a random point. Okay? And, okay, maybe I should, okay. If you want just one, okay, maybe not. Okay, I wanted to give you a serious inequality, but too bad, it's painful. So let me just close with this. So now you can probably open the paper, and it's not too long. Again, the papers before where we did the Langevin dynamics were really painful technically. This one is not. This is why we isolated the OGD case. And by the way, we did the Langevin and gradient flow for tensor PCA, but not for the general class of GLMs. And that we can now use, but and going in the direction that we just discussed, going for larger batches and this kind of thing. But it's a pain. It's a little, it will come out someday. Now, let me give you another example of, I will conclude with just publicity for a different, I have 10 minutes, right? Okay. Yeah. Something else, which is in the other direction. It's the direction of refutation. And so it's a recent work on Sparse Pca with Ilyas Zadik. Maybe alphabetically that's Alex Vine, Ilyas Zadik, for both postdocs at Courant or at CDS, for Ilyas, at the Center for Data Science at NYU. And so we do the following. So we look at Sparse Pca. It's a very studied problem, but interesting. And now I'm coming back to the idea of complexity, right? What I've just done is to tell you, even though I've been talking about complexity for a while, we shouldn't be obsessed by that, because in fact there's another problem first, which is escaping entropy. Now I'm coming back to questions of complexity. But in a context where you cannot use the tools of Morse theory, of cat's rice, etc. Right? Because when can you use cat's rice and all these things? It's when your variables are continuous. Also, right? Here, there, that's why I chose to be on the sphere, on RD. If your variables are discrete, what is a critical point? I'm sorry? No. There are limitations to cat's rice, I understand. But I'm saying I'm looking at other, not even being able to say, because what is a harmonic minimum? Sorry? What is a discrete harmonic critical point? What is a discrete critical point? This is hard. In fact, the notion exists, but it asks for way more topology. But Morse theory exists for discrete functions, but on specific spaces, which are called CW complexes. So for instance, when you take the usual discrete space, plus or minus 1 to the n, hypercube, in order to do a proper notion of critical points, you have to extend it to the full complex. That is the vertices, the sides, the edges, the sides, and the full cube. Right? So you have to, in some sense, extend your function to this. So going this way is a little hard. But the idea of complexity is still there, even if you have a discrete landscape. Right? So here is an example for this sparse PCA. So what is sparse PCA? You have a GOE matrix that I call W, and as before, you have a spike that you want to find with a signal-to-noise ratio and a K here. So this is a K here is a vector, is a K-sparse vector X here in, let's say, 0, 1, it could be, to the n. This is an n by n GOE matrix. Okay? So it's really PCA. You have a vector, you have noise. This is rank 1. And X is K-sparse, which of course means you have only K coordinates of X which are 1. Okay? And so n will be tending to infinity here, and our lambda might be a lambda of n, the signal-to-noise ratio. Our K might be a K of n. That's sparsity. Okay? And you ask the PCA problem, that is, recover X, right, from a sample of Y's. Okay? So if this was, if I don't have this information and don't want to recover a signal that is sparse, but just have a vector here and a GOE matrix, if this is just, if you want, if the prior on my X is nothing, let's say X is just a unit vector, so which I choose uniformly on the sphere, if I know nothing about it, then this is BBP transition. Right? Here it's different because the prior here is not uniform on the sphere. It's a K-sparse vector that you don't know on 0, 1. And of course, the estimate you want to recover has to be K-sparse. Okay, so this problem has a long history. But X is given and you don't know. Right? That's so what do we know here? And what we're asking for, we want here maybe exact recovery or close to exact recovery. Of course, you could have partial recovery. BBP helps indeed for partial recovery, but here I want a little more precise. So there's a hard regime for that. That's well known. And the hard regime is when lambda is between square root of K over n and so, and then there's a conjecture which is that in the hard regime, any algorithm, essentially, of course, what does that mean? For exact recovery, require a time which is very long, requires the time which is exponential of constant k square over lambda square n, which is in this regime is long. Okay, so there is recent work on this hard regime, and in particular a paper last year by Ding Kunitsky, PhD student at NYU, the same Alex Vine, and Alfonso, where this thing is achieved. This time is defined one algorithm that achieves that. So this algorithm has two phases. There's first a kind of exhaustive search and then some kind of boosting. I won't go there. So the question is, all right, there is one algorithm doing that, but maybe there are better things to do. So here the question is, in this hard regime that is left is the refutation, that is to prove that essentially you cannot really do better. So what we prove in this work, we prove that in fact, when you are in the hard regime, So that in this work with Alex and Elias, we are in the hard regime, plus another condition which is there for whatever reason. It's a part only of the hard regime. There exists a free energy well. Of depth, exactly what we. The same depth. Where did I put it here? K squared over lambda squared over n. This with high probability. This is, of course, a very informal statement, but I don't want to give the exact theorem. So this tells you that in this landscape, you really have a barrier to cross, which is of that height, and so the time to do it has to be long. Okay, so I wanted to close on this because this is very far. Here you don't have the notion of Morse function, critical point landscape, saddle points, and whatever. But still, this is just a word of caution. I've insisted a lot of entropy. Complexity is still there. When you have barriers to cross, you have barriers to cross. So this, in this case, it happens. And it is not, honestly, I don't know how to put that in the framework. So this is just saying that I don't understand things. I don't know how to put that in framework of the complexity I was describing before. But I'm completely sure that this landscape, here we just say something very minimal. There is a barrier to cross, so it will be long. But I'm completely sure that in some sense, the landscape of this thing in the hard regime is very complex. There is not only one barrier, the whole landscape is crazy. But I don't even know how to say it, really. Okay, and I will stop here. This is also just this year.